Another situation where we find a magnetic dipole. Well, who can tell me? Where else have we seen, or where else have you seen, maybe in previous experiences, a magnetic field pattern that looks kind of like that? What else produces a magnetic field pattern that looks like a dipole field? A bar magnet. Yeah, a bar magnet produces the same sort of pattern. And a bar magnet, so here's a bar magnet, and it's producing a magnetic field that at one end is kind of pointing away, and then it kind of spreads around, changes direction, points in the opposite direction here. And then at the other end, the field tends to point towards that end of the bar magnet, and again, it kind of spreads around and points in that direction. So this is the field pattern due to a bar magnet. And so the end of the bar magnet where the field tends to point away is a special name. That pole is called what pole? Is that the north or south? That's the north. Yeah, the north by definition. So the north pole, magnetic field tends to point away from it. South pole, magnetic field tends to point toward it. Okay, so that's a bar magnet. So we've all seen this, right? So here's a bar magnet, and I don't know if it's powerful enough to stick to the. It sort of wants to, but it's a bit too heavy. There's a steel backing behind the whiteboard, and sometimes you can get it to stick. But we've all seen this. The question is, why does a bar magnet make a magnetic field that looks like this? I mean, are there any moving charges here? Are there any currents here? Doesn't appear to be. It's not hooked up to a battery. So what could possibly be making this magnetic field? Any ideas? Well, what's at the center, or what's inside? What's it made of? Okay, so there's mobile electrons. There's electron C. But so maybe electrons do have something to do with this. So what would the electrons have to be doing in order to make? They'd have to be orbiting. Yeah, they'd have to be orbiting. Where do we find orbiting electrons? In atoms, right. We have to have a situation where there in fact are mobile charges. There are charges that are moving in a particular way. There are electrons that are moving around inside the atom. So what will we have to have? Well, let's just look at a single atom. We have a nucleus, of course, very tiny compared to the size of the atom. We have a shell of inner electrons, which are all orbiting in such a way as to add up to a net. Essentially, we say the net angular momentum is 0 for the inner electrons. But for most metals, we have a single sort of outer electron, which we can model as orbiting the inner electrons plus nucleus. Okay, so essentially it's like having just a single electron orbiting the entire atom. Okay, kind of like hydrogen, only we're kind of ignoring the contribution, or saying the net contribution of all the inner electrons sums up to 0. So if you have let's see if we can draw this out. Let me draw this a little bit bigger. If you had a single atom, and in our sort of simple model, this of course is not an exact picture of what's going on, but just kind of a simple model to give us a sense of what's going on. Let's say the electron is going into the board at the top, coming out towards us at the bottom. So that would be the direction of the electron current. So the conventional current would be flowing opposite direction, right? So capital I would be coming out towards us at the top and going in at the bottom. And so that would produce, if we had an electron moving in that direction, a magnetic field, a dipole pattern of magnetic field, exactly the same way as we were drawing the field due to the the current loop before. Okay. Well, it's not just one atom. There are lots of atoms in this bar magnet, right? But essentially, what do we have to have in order to get a net magnetic field? What has to be true about the motion of those electrons? It has to be uniform. They all have to be lined up in a particular way, right? If you had one atom where the electron's orbiting like that, and another atom next to it where the electron's orbiting maybe like that, and another atom next to it with the electrons like that, another atom next to it with the electrons like that, are you going to see a net magnetic field? No. Okay? So we must have a situation where, at least to a first approximation, we'll get a little bit more detailed in a second, we must have a situation where all the atoms have their electrons lined up in such a way that they're all orbiting in the same direction, and then we say, okay, each electron produces a magnetic field, and so we add up the magnetic field due to all those atoms, and there are a lot of them, and we get a net magnetic field due to the motion of all those atoms. Okay, and now we still haven't answered why there are only certain metals that seem to do this, right? Only iron, nickel, cobalt, maybe a couple other rare earth elements. So it's certainly not a universal case that we can get this to happen all the time. But let's at least see if we can figure out, coming back to this idea, if I want the net dipole moment of the bar magnet, in other words, this mu factor is measuring essentially the strength of the dipole, how big of a magnetic field it's going to produce. If I can find, just as I had here, if I had the dipole moment of one coil, I can just add up the dipole moments or multiply by the number of coils we have and get the total dipole moment of the coil. I'm going to try to do the same thing here. If I can find the dipole moment, magnetic dipole moment of one atom, and then figure out the number of atoms, I should be able to at least get a reasonable estimate for the dipole moment of the bar magnet. Okay? So let's see if we can work out the dipole moment, magnetic dipole moment of a single atom. So let's come back to this simple model. Here's our inner electrons plus nucleus, and here's our orbiting atom, or orbiting electron, excuse me. And we'll say the electron's moving in that direction, some speed v, and that's a distance r. And we said that mu, by definition, is the current times the area. Okay. Well, what's the area? Pi r squared. Do we know how big r is? Approximately. How big is r? The radius of an atom. What's the approximate radius of an atom? An angstrom. Yeah, an angstrom is about 1 times 10 to the negative 10 meters. Yeah. Okay. All atoms, roughly speaking, have about that size of a radius. Okay. It varies, of course, from element to element, but that's at least a rough approximation that we can use. What about the current? Well, the current is the amount of charge flowing per unit time. Well, how much charge do we have flowing? Yeah, 1 electron charge, right? 1.6 times 10 to the minus 19. What's the time that we're interested in? Yeah, the time it takes to make one orbit, right? So we want the orbital period. Okay, so E over T. Well, there's a couple ways we could calculate out the period. One way is to do it purely classically, and you could work out using the laws of mechanics how fast it's moving around if you know the radius and you know the electric force, just based on basically thinking about the perpendicular component of the rate of change of momentum or centripetal acceleration, depending on how you may have seen it in your 205 class. I'm going to do a slightly different approach and use some more modern ideas of what we know about atoms. Let's say that, okay, the speed of an atom, if it's moving around a circle, is going to be the circumference divided by the period, so 2 pi r over t. And then the period is then 2 pi r over v. We plug that back in here, and so we have the current then being equal to E over, or E times V over 2 pi r. And then I can plug that back into our equation for mu. So I have the current, which is EV over 2 pi r. And I have the area, which is pi r squared. So pi's cancel, one factor of r cancels. And we're left with 1/2 EV times r. Well, rather than put it in terms of the velocity, I'm going to use something I know about angular momentum. First of all, does anybody remember the definition for angular momentum? An angular momentum of a particle in orbit. Orbital angular momentum or translational angular momentum, depending on how you've heard it. What does it depend on? Well, the angular momentum principle says that if there is a torque, the angular momentum would change, right? But we just want to figure out, if you know something's moving around the circle, you know the radius, you know the speed, how do you determine the angular momentum? A review of mechanics. Okay, then the name suggests it might depend on the mass. And mass and velocity make up, not force, momentum. Okay, so there's a momentum in this direction, a p vector in that direction. So angular momentum depends on the linear momentum and, the distance, right? The perpendicular distance, right? That moment arm, sometimes it's called. And so here's a vector, r, that points from the center to the mass that's moving, and it's perpendicular to the momentum. And so the formal definition is R cross P. Does it look familiar to people? Yes, a couple of nods. Okay. All I want's the magnitude of this thing. So that's just the magnitude of R, which is just capital R, the radius, times the magnitude of P, which is just going to be the mass of the electron times its speed. So let me say that V then, solving for this, V is equal to L divided by R times M. Okay? Plug that back into here. Mu is equal to E 1/2. I have E, I have L over Rm times R. So in fact the R is going to cancel out. I have 1/2 E over M times L. So what this tells us is that the dipole moment for a single atom in orbit around, or single electron, in orbit around the atom, is 1/2 electron charge divided by electron mass, those are constants, times its angular momentum, its orbital or translational angular momentum as it's revolving around the center of the atom. Well, there's a special property about angular momentum that some of you may know, depending on, you may have seen it in 205, you may have seen it in the chemistry class, but it has to do with our modern understanding of the atom. And we know that in an atom, first of all, we know something about the energy, right? Energy in atoms is what? What's the magic word? Okay, it's conserved, but it's also, someone said, quantized, which means you can only take certain values, right? Well, that's true also for angular momentum. The angular momentum of an atom is quantized. And in the simplest model, this angular momentum is equal to just an integer times a constant, h bar. Does anybody know what that is? That's Planck's constant. That's the Planck divided by 2 pi, right? So Planck's constant h divided by 2 pi. So this is Planck's constant. So this is a fundamental constant of nature. It's essentially giving us the smallest unit of angular momentum that you can possibly have, and it occurs in units of this h bar. And this number is equal to 1.05 times 10 to the minus 34, and the units are joules times seconds. So let's calculate out the magnetic dipole moment of a single atom, an electron in orbit around a single atom. So we have mu is equal to 1/2 E over m, and if it's in its lowest angular momentum state, it's just going to have an angular momentum of h bar. So it's 1/2. The charge is 1.6 times 10 to the minus 19 coulombs. The mass is 9.1 times 10 to the minus 31 kilograms, mass of an electron. We have 1.05 times 10 to the minus 34 joules times seconds. Sorry, joules times seconds. Say again. Would the charge be negative? We're just looking for the magnitude of this thing. Okay, it's going to have some direction. We can figure out the direction based on the orbit of the electron and how the bar magnet's lined up. So let's just look for the magnitude. Okay. Okay, so plug it in. What do you get? Calculate it out. Break out a calculator. Try it out. See what you get. And while I'm doing that, while you're doing that, I'll get this question ready. (9.2) times 10 to the negative, what was the exponent? 24? Okay. Anybody else get something similar? Agree? Disagree? Look okay? Got it? Okay, sounds good. What are the units? I'm not going to go through and do all the unit conversion here, but we can go back to the original definition and see that the units have to be units of current. Units of current are, what's the unit of current? Conventional current? Amps times units of area, which would be meters squared. Okay, so this is in amps meters squared. Okay. This is an approximation anyway. We're using a very sort of simple model here, so I'm just going to round this to 1 times 10 to the negative 23 amps meters squared. Okay. Great. We've got the magnetic dipole moment of one atom. How would we relate this to the magnetic dipole moment of the entire bar magnet? What would we need to do? What would we need to know? Okay, so you need to know the weight and the atomic mass, right? Because ultimately what we want is those things are going to give us the total number of atoms, the total number of atoms. Okay, so here's a question. Here's a question. We estimated the mu of one atom to be 1 times 10 to the minus 23 amp meters squared. The mass of the magnet is 13 grams. Okay, so this is an approximate mass of one of these little bar magnets that you might see in the experiments you're doing in the lab. So something that looks kind of like that. This actually will stick to the wall. And the atomic mass of iron, we will assume that this bar magnet, which is an alloy called alnico, so it's iron, but it's got some aluminum, nickel, and cobalt mixed in, but it's mostly iron. We'll say that the atomic mass is 56. How do we predict the magnetic dipole moment of the entire magnet? So there are some expressions there. See if you can work it out. Might be the best thing to do might be to try to work out how you would calculate the number of atoms and then see which one agrees with your calculation. Okay, so we are converging to an answer. It's got to be answer 5, right? 13 grams times the number of atoms in a mole divided by 56 grams per mole, right? So it's just it's sort of just a unit conversion problem. If you want the number of atoms, you can say that it's going to be the mass, 13 grams. You have 1 mole for every 56 grams. That's what the atomic number means for iron. And then we can just convert moles into the number of atoms. So 6 times 10 to the 23 divided by 1 mole. That gives you the number of atoms. And so if you want that times the magnetic dipole moment of the entire bar magnet, you'd have mu of 1 atom times that. And so we get this all multiplied by 1 times 10 to the minus 23 amp meters squared. So work it out. What are you going to get? Calculate it. What do you get for the... Okay, so 1.4, and the units are amp meters squared. You get an ordinary looking number because you have a dipole moment that's on the order for per atom, that's on the order of 10 to the minus 23, but then you multiply that by the number of atoms in a mole, which is 10 to the 23, and they cancel out, and you get a number that's kind of ordinary looking.